So if you go to the terrestrial planets, the situation is quite different. So the D/H ratio on the terrestrial planets in water is quite different from what we know from the outer planets. So for instance, in Mars, the value in the water is known. From the outer planets, basically, we do not know the D/H ratio in water. And on the other hand, on the terrestrial planets, we do not know the D/H ratio in hydrogen, at least not in the atmosphere. And so what we measure remotely, for instance, the D/H ratio in the water, but also maybe in Mars, meteorites and so on. If you speak about Mars, we have a D/H ratio of about, in meteorites, of about 300 ppm. But in the atmosphere is much higher than that, maybe 2.5 times higher than that. The reason is escape of the atmosphere. So the Mars atmosphere originally had a much higher density, but with the time the atmosphere eroded, so to speak. That is believed, at least one of the theory, meaning that the lighter elements escape via thermal escape, and then the chance that a normal hydrogen atom escaped was higher than a deuterium atom. And so in that sense, we got an enrichment of deuterium, which is 5 times the value we have on Earth. On Earth, the value is about 155 ppm. That is what we measure everywhere in the water, which is called also the so-called VSMO value for Vienna Standard Mean Ocean Water. And this is some kind of reference we are using for characterizing the DOVH in other objects. Then if you go to Venus, we have a huge enrichment, which depends it depends on who is measuring that. There are different methods how to measure that, radio astronomical methods, or methods from satellites in the millimeter wave, in the submillimeter wave, in the UV, in the infrared. Mainly in the infrared, we get values which are enriched by a factor of 150 to 250 compared to Earth. So extremely high values. Of course, this is processed, and that doesn't tell us so much about the formation of the solar system. Different, of course, is the situation if we investigate material which is primordial. And primordial material is believed to be still present in comets, since comets come from the outer solar system, where very little processing took place over the year, and so this material is called pristine. And so therefore, it's very interesting to investigate the D/H ratio in comets. And the first time this happened in, I think, 1986 during the Giotto mission, so the first European, I think, cornerstone mission of the European Space Agency, flying to Halley's Comet. And with in situ measurement, the D/H ratio was determined to be 2 times the D/H ratio on Earth. Before, people believed that comets may have brought water to Earth, and that most of the volatiles we have on Earth stem from comets. But this result showed basically the opposite, or not, we cannot say the opposite, but showed that it cannot be true, because D/H just didn't fit. So this kind of fingerprint pointed into the different direction. And so since then, people tried to measure the D/H ratio in as many comets as possible. And indeed, by ground-based observation, by telescopic observation, it was possible to measure DOVH in at least 5 different comets. For instance, the comet Hyakutake, the comet Hale-Bopp, and a few other comets which were very bright. But the problem is to measure DOVH from ground, from the Earth. You need a very bright comet with a high production rate of water vapor. So we speak about, let's say, something about at least 10 to the 28 molecules per second, so about 300 kilogram of water vapor production per second, maybe more. Hale-Bopp had basically even a factor of 1,000 more. And if that is the case, that the comet is extremely bright and we have extremely lots of water production, we have also the chance to measure the weak isotope, like HDO. So that was done by a couple of comets, but it was never possible to measure that in a Jupiter family comet. The reason is that they have relatively short orbits. The Jupiter family comets are short period comets, maybe with orbital period between 5 and 20 years. I think Hale-Bopp had a couple of 1,000 years, or Halley has about 80 years. So if comets have short period orbits, it means they're exposed to the sun in general many times in relatively short time scales. That means they come near to the sun, and then they lose lots of their volatiles, and therefore with the time they are less bright. In general, they are much smaller than comets from the Oort cloud. So Oort cloud comets, which is far out and maybe up to 10,000 astronomical units, while Oort cloud comets maybe, while Jupiter family comets, they go out only, as the name says, not somewhere between the orbit of Jupiter and Saturn. And so since that is the case, the problem is to measure the D/H in the Jupiter family comet. And we took the advantage of a space telescope called Herschel Space Observatory, which had a high resolution instrument called heterodyne instrument for the far infrared. And this instrument is extremely sensitive specifically to water. I mean, the cometary spectra of water are extremely narrow. And if you want to detect them, you need extremely high spectral resolution. And HiFi had a spectral resolution of about 10 millions. And so at the same time, it had detectors working at the quantum limit, at the physical limit. And then in space, so without a disturbing atmosphere in between, we were able to measure for the first time the D/H ratio in a Jupiter family comet. And that was planned from the beginning, so we were involved in this Herschel mission since early 90s. We were involved in building instruments and so on. It was launched in the year 2009. And then in 2010, we performed this observation of a Jupiter family comet called 103P Hartley 2. And but maybe some people know Hartley 2 also from the epoxy mission. There was an American spacecraft which made some nice photos and did a lot of investigations. Also in 2010 when it was near perihelion. And at this time we did our observation of HDO together with H216O and H218O. Why H216O and H218O? Because H216O is an optically thick line, and if you want to determine a ratio, you have to make sure that you see the same volume, the same amount of molecules, so to speak, and that requires that the lines are optically thin. Therefore, we measured H218O to HDO and at the same time related it to H216O. But the main measurement was H218O to HDO. And from this observation, we learned that the D/H ratio in this specific Jupiter family comet was telluric. That means the same than on Earth. So we showed that this conclusion that comets could not have brought water to Earth is not true, because at least we have found one who has exactly the same D/H ratio than what we find on Earth. Anyway, it's a very difficult measurement, and with Herschel we were able to measure one more comet. And this comet, the HDO was very weak, so we even didn't detect it. We got an upper limit, which was not much above the D/H ratio measured in this comet Hartley 2. And of course, for the future, it would be very important, it's very interesting to measure D/H in a as large as possible sample of comets. And one more observation will be performed quite soon with the Rosetta mission, in situ determination of D/H. And then we have to look into the future, what is possible. One possibility maybe is the Atacama Large Millimeter Array. There may be some observations possible, or another submillimeter telescope like CCAT in the Atacama Desert. Then there's a Russian experiment called Millimetron, which is extremely sensitive, and with that it should be easy to measure a large number of Jupiter family comets and determine the D/H ratio. So maybe there are some future in situ missions to comets, so some missions are discussed but not selected yet. Anyway, it's a very, very difficult measurement, and I personally hope that at least the missions which are discussed now will also be realized and give us the opportunity to get a larger sample, not only of D/H ratio in Jupiter family comets, but also in Oort cloud comets, because we just have 5 or 6. Of course, the D/H ratio is not the only criterion from which we can see whether water was delivered to Earth by comets. There are also other isotopic ratios which will be determined now by the Rosetta mission, like the N15 to N14, so nitrogen 15 to 14. So this has been determined also in a number of comets by ground-based observation, but mainly in HCN. Recently also in NH2, but the question is whether that is representative or whether most of the nitrogen, for instance, is in form of N2. Another important aspect in this sense is the amount of organics in comets, because usually deuterium is enriched even higher in organics than in water, and the Rosetta mission will provide all this kind of information. So what is the D/H ratio in the comet? What is maybe the D/H ratio in the organics? What is the amount of organics relative to the ices and the silicates? So that means the Rosetta mission will really provide or will be a big step forward to learn more about this topic, whether comets brought water to Earth.